In this paper, we introduce a universal technique for real-time localized photorealistic video style transfer. Given an input content video and its object segmentation mask, our method learns to transfer different styles to different local regions while preserving the photorealism and temporal consistency. We first aim to transfer the style from a set of images to two different local regions that we call foreground and background. Blending in the pixel space results in unnatural object boundary due to the hard edge in the mask. Our network architecture builds upon the work of bilateral photo style transfer, which learns local age-aware affine transformed from low-resolution content and style inputs, with the result sliced out from a compact transfer representation at the full resolution. However, this does not work well on the localized style transfer learning due to the three reasons. First, content statistics upon which stylization operates need to be localized and temporally coherent to produce a satisfactory output. Second, pixel space blending using object mask depends critically on mask quality. Lastly, we find that without additional temporal regularization, there is noticeable flicker in the stylized video. We replaced the learned lookup table with a two-layer convolutional neural network that also incorporates the object mask to learn an adaptive guide map that better separates foreground and background. We used the adaptive guide map to build a soft grid space mask and generate a blended grid to render the output at each pixel. Our grid space blending can render smoother boundaries, but the foreground style bleeds to the background. We address this with a spatially aware AdalN, which extends the operator to account for the content mask. With the proposed spatially aware AdalN, our model can separate the foreground and background styles well and render high-quality object boundaries. To handle imperfect segmentation masks, our algorithm learns an enhancement network to improve the boundary of masks. With the three introduced techniques, our model better separates foreground and background at boundaries and avoids the classic halo artifact. Next, we tackle motion. Although using AdalN has shown to be effective for still photo style transfer, it has been shown that these features are sensitive to small changes in the input. To address this, we propose a temporally coherent AdalN layer that computes the mean and variance from both the previous and current frames. Combining spatially aware AdalN and temporally coherent AdalN, we obtain a differentiable spatial-temporal feature transfer layer that is able to transfer style to local regions and generate temporally coherent stylized videos. Our model consists of two paths. The grid prediction path consumes low-resolution content, style, and masks, and infer a bilateral grid that encodes how to transfer each layer. At full resolution, we predict a guide map that tells us how to best blend the style transforms as well as how to index into it for rendering. We augment the content style fidelity loss and the bilateral space Laplacian regularizer with three new losses, including mask loss, guide loss, and temporal loss. We compare our method to four state-of-art photorealistic style transfer algorithms. To make the comparison more fair, we apply a temporal consistency post-processing to improve their results. Our method generates more visually pleasing stylized results than baselines. Our method is much faster than all but the method of bilateral photo style transfer upon which it is based. Still, our model can run in real time on 12-megapixel inputs, while other approaches run out of memory. Moreover, we conducted a user study to judge whether our method delivers subjectively better results compared to the baseline. For each output, the users were asked to rate three questions regarding stylization, visual artifacts, and temporal stability respectively. This table shows the percentage that our result is preferred over the other. Overall, our method is selected on more than 60% of comparisons of all three questions. Here's an example that we transfer different styles onto foreground and background of a rose video. Our method can easily transist between different styles in time by interpolating between predict grids using an appropriate time-dependent weighting function.